In this episode of Remote College Algebra, we'll be working on becoming equation-solving gurus. At first, we're going to point out a couple of things not to do, because part of being a guru is to know what not to do. For example, you cannot distribute a power over a sum or a difference. So for example, x plus y to any power is never going to equal x to that power plus y to that power, unless that power is 1. If it is 1, then that's the exception. So for example, 4 plus 9 squared is not 16 plus 81. We know that 4 plus 9 is 13, and 13 squared is 169. You're not going to get 169 if you add 16 and 81 together. 4 plus 9 is still 13, and the square root of 13 is not going to equal 5. So it never works to distribute a power over a sum or a difference. Again, unless the power is 1. If the power is 1, that's an exception. Another thing to avoid is canceling when you cannot cancel. So you cancel when you are multiplying factors. And the reason things cancel is because they actually divide out. So for example, here I have 2 times p times x plus 2 being divided by 4 times p squared times x plus 5. 4 is 2 times 2, and p squared is p times p. Notice I have 2 multiplying p multiplying x plus 2, and 2 multiplying p multiplying x plus 5. 2 divided by 2 is 1. So we divide those out because they're basically just equivalent to 1, and 1 times anything doesn't change the value of it. P divided by p also will be 1 because you assume it's the same value. So again, we can divide those out. But I can't divide out this x with that x, because this x is being added to that 2, thus creating this whole factor. And x down here is being added to 5, creating a different factor. So in this case, only the 2's and only one set of 2's and one set of p's divide out. And you can see in these other examples of wrong things to do. So part of solving equations is to recognize what is actually legal and correct and what is not legal. Down here I have this polynomial factor of x squared plus 3x minus 10. Yes, there's a matching factor down here in that polynomial being squared, but notice this term that is being subtracted does not have that factor in it. So I cannot divide this factor into this factor, because I would be completely ignoring that this term is being divided by that polynomial squared, not that polynomial to the first power. So it is wrong to rewrite this big expression as the one over here, where I've canceled this polynomial with one of the ones here. This is a wrong thing to do. And you also want to recognize that 2 times 3 squared is going to be 2 times 9, or 18. It is not 6 squared. So exponents, you calculate them first and then you do any multiplying or dividing. So 4.5 times 10 to the x is just going to stay 4.5 times 10 to the x. It's not going to turn into 45 to the x, because the 4.5 is not being raised to the x, just the 10 is. And over here, e to the x being squared is not e to the x squared. Instead, the rules of exponents tell you to multiply those exponents together. And so this would end up equaling e to the 2 times x. That is the correct thing. Alright, so obviously there's infinitely many wrong things I could show you. This is just a little collection of things to pay attention to that you're not doing. So starting off our trek on solving all kinds of equations, we're first going to focus on how solving any equation is undoing the operations that are being done to your variable. And you are undoing those operations. So the basic order of operations are you do what's in parentheses first, then you deal with any exponents, then you deal with any multiplying and dividing. And the order of multiplying and dividing doesn't matter. You don't have to do multiplying before dividing, but you do the process of either multiplying or dividing after you've looked at any exponents, after you've completed what was in parentheses. And then lastly, you deal with any adding and subtracting. When you're solving equations, you work that backwards because you're undoing. So you first want to deal with any adding and subtracting. So in this case, I have 2 being added to that front term. So I want to subtract 2. So we have 2.5 times 3x minus 4 squared. And 2 is being added. I'm going to subtract 2. And whatever I do to one side, I have to do the same thing to the other side. So that gives me negative 2.5 times 3x minus 4 squared, and I will get a negative 1 on that other side now. Then I'm going to undo any multiplying and dividing. So I have a 2.5 multiplying the expression that has the variable, so I'm going to divide by negative 2.5. So I divide over here by negative 2.5. And that will give me 3x minus 4 squared equals positive 1 over 2.5. And 2.5 is 5/2. So the reciprocal of 5/2 will be 2/5. So I think I'll go ahead and write it that way. Now I am going to undo the exponent. I'm going to cancel out the square. So taking the square root, I end up with just 3x minus 4. And on this side, I will have the square root of 2/5, which is not a nice number, so I'll just leave it in exact form. Now, when you undo an even power, in the set of real numbers, what was being squared could have been positive or could have been negative. So when you're generally solving an equation, unless there's some word problem or some issue in which you know you're only dealing with positives or dealing with negatives, you should express that this could have been positive square root of 2/5 or the opposite of the square root of 2/5. I'm still trying to solve for x, so I now want to add 4, so I will get 3x is equal to the square root of 2/5 plus 4, or negative square root of 2/5 plus 4. And then, to get x completely isolated, I will divide that by 3. So I will get whatever the square root of 2/5 plus 4 is divided by 3, or whatever the opposite of the square root of 2/5 plus 4 is divided by 3. So what I'm finding, and I'll get some decimal approximations for those answers. Right now they're in exact form, and they are the exact answers. What we're finding are these 2 intersection points. And so I can see I do have 2 solutions. If I take the square root of 2/5 and I add 4, and then I divide by 3, and I take the opposite of the square root of 2/5 and I add 4, and I divide by 3, I get 1.54 approximately and 1.1225 approximately. So looking at our graph, I have, this one must be the 1.1225, and this one must be the 1.5442. 2 if I want to keep carrying things out. So notice 2 answers between 1 and 2, so my solutions make sense from the graph. All right, so again, they're not nice clean solutions, but the process stays the same whether you get nice answers or you get messy answers. So again, that's applying to a problem that's kind of built right out of the order of operations. Here's another one in which you could look at it just as the order of operations. The square root is the same as a 1/2 power actually. You could rewrite this as 7x minus 12 to the 1/2 power. And I don't have any outside adding, I don't have any outside multiplying or dividing. And so the first thing to undo is that power. So I want to use the reciprocal power. That's actually what a square and a square root are. They're inverse functions of each other. They're reciprocal powers. So 7x minus 12 to the 1/2. If I raise that to the second power and you multiply those powers together, you're going to get 1. But whatever I do to one side, I have to do the same thing to the other side. And so on this side, I will get 20 squared, which is 400. So we get 7x minus 12 is equal to 400. Now here I was undoing a square root and not a square. And so I only will get a positive answer. You could see from the graph that there's only one answer. And it's because the square root will always be positive. So 7x then will equal 400 plus 12 because I'm canceling subtracting 12 by adding, and that will give me 7x is equal to 412. And then lastly, divide by 7, and we end up with x equals 412 sevenths. Again, that's the exact answer. If we wanted a decimal approximation, it is approximately 58.857. And looking at our graph, I can see that intersection point right here. It's just before I get to 60, so 58.857. That is the x coordinate. The y coordinate is 20. We were trying to set this equal to 20. All right. Another example in which you can just look at it is undoing the order of operations. Here we could imagine that we're investing $1,776 and we are investing it in a CD that gives us interest every month. So our interest rate would be divided by 12 months, and I'm going to keep the money in there for 5 years. So 60 months is 5 years. I'm hoping to grow my account to $2,800. So I want to know what kind of rate I would need in order to have my money grow to $2,800. So I don't have any outside adding. I do have some outside multiplying. So I'm going to divide both sides by that 1,776. And when I divide this side by the 1,776, I get 2,800 divided by 1,776. Those divide out to be 1, and we get 1 plus r over 12 to the 60th power is equal to whatever that fraction is. I'm just going to leave it in that fraction form for right now. You're better off leaving things in exact form until the very end, and then you can round, and that way you know that your answer has stayed exact up until the, wherever decimal place you need to round it to. Okay, I'm trying to undo this power. So I'm going to use the rules of exponents, and the rules of exponents say if I raise a power to a power, I multiply those powers together. So if I want to reduce that to a power of 1, I need to use the reciprocal power. So I'm going to raise to the 1 over 60 power because when I multiply those together, I will just get 1 plus r over 12. But whatever I do to one side, I have to do the same thing to the other side. So my fraction over here also is going to get raised to the 1 over 60 power. So that gives me 1 plus r divided by 12 is equal to whatever that fraction is to the 1 over 60 power. And I'm still trying to get r. I don't have r quite yet. So I want to undo the adding. Remember, you're going to do the order of operations reverse. So subtract 1 from both sides, and that will give me r over 12 equals whatever that fraction is. We will round it in the very end. And now, to finally get r completely by itself, I'm going to multiply by 12. And I get r is equal to that, okay? So it's this messy fraction raised to the 1/60th power minus 1, and then I will multiply that by 12. So that sounds like a good job for my calculator. If you have one of these graphing calculators, you could actually type that whole thing in if you're careful. So 12, I'm going to put a parenthesis to imply multiplication. 2800 divided by 1776, and I'm raising that to the 1 over 60 power. I need parentheses around the 1 over 60, otherwise it'll raise it to the first power, and then it will divide that answer by 60. That's not what I want. I want the exponent to be 1 over 60. Then I subtract 1. I need to close my parentheses so the 1 also gets multiplied by the 12. And we get an interest rate of 0.09139, which is actually, for this day and age right now, it's high. But we can always dream. So I would need a 9.139% interest rate to actually have my money grow to be $2,800 in only 5 years. So I probably either want to somehow get some more money to put in my account or wait a little bit longer. We can see here in the graph, this was the curve that was plotting 1,776 times 1 plus r over 12 to the 60th. That's that function. So if I graphed y equals this, I would get this red curve. And then I set it equal to $2,800. And you can see that our intersection's between 0.06 and 0.1, so we found it to be 0.09, or that 9% interest rate. Not every equation can be done by just purely marching through the order of operations in reverse order. Sometimes you have to manipulate things a little bit before you actually get it to the stage where you are just undoing the order of operations. This is an example. I have variables on both sides. The variables are trapped in sums or differences, and then they're trapped underneath square roots. So I have to do some unraveling of that before I can really just see that I'm undoing the order of operations. I will start by taking the square of both sides, because that will help me cancel out the square root or the 1/2 power. But careful when you're squaring that left side. I'm squaring both sides of the equation, and so I'm going to have to actually FOIL that left side. Now on the right side, when I square, it does just get rid of the square root. So on this side, we nicely just get 4x plus 67.5. But on the other side, it's going to be quite a mess. In fact, I don't know if I even have room in the amount of space that I left there. But we'll get it started. what we're doing is, again, we're taking the square root and it's added to 6.5, and then we're multiplying that by itself because we're squaring. So there's going to be a second square root plus 6.5. So I have a binomial here. It's just kind of a unfamiliar binomial. So you're going to FOIL. I'm going to multiply the first, and then the outer, and then the inner, and then the last. And so because I have the same thing under both of those square roots, I mean, they're both 2x minus 8. When I multiply those two together, I will get 2x minus 8. And then I will get 6.5 times the square root of 2x minus 8 plus a second 6.5 times the square root of 2x minus 8. And then I will get 6.5 squared, and that is equal to 4x plus 67.5. Okay, so yes, quite a mess, but we will continue to clean it up. So 2x minus 8, 6.5 and 6.5 add to be 13. So these are both like terms. They're both involving a square root of 2x minus 8. So I can add them together, and then 6.5 squared is 42.25. And then that is still equal to our 4x plus 67.5. Okay, so what can we do here? Well, let's try to collect like terms. So my 2x is like the 4x, so I'm going to subtract 2x from both sides, and I get negative 8 plus the 13, 2x minus 8 plus the 42.25, and on this side 4x minus 2x is 2x. Okay, so now I want to still collect like terms, so a negative 8 is like that 42.25, and their numbers, and the 67.5 is a number. Why don't we first combine the negative 8 and the 42.25, and you get positive 34.25. Alright, it's starting to look a little bit better. So then subtract 34.25 from both sides, and you will get 13 times the square root of 2x minus 8 plus 34.25. And on this side, 67.5 minus 32.25 is 35.25. Or actually, sorry, it was 34.25. So 67.5 minus 34.25 is 33.25. I guess I could have figured that out because it was only off by 1. Okay, so again, where that Where that 33.25 came from is I subtracted the 34.25 from both sides. And here we go, that's going to be gone. And now we have this. And if we get a second piece of paper to keep going here. Now I'm going to need to square both sides again because of the square root. So I could divide by 13 if I really wanted to, but it's certainly not going to make it any cleaner. But legally you could do that. But 2 divided by 13 is not going to be nice, and 33.25 divided by 13 is not going to be nice. So we might as well just leave it and square both sides as we have it. So 13 times 13 is 169, and when I square the square root, I will get what was in the square root, because the square root and a 2 are inverse functions. And then once again, I'm going to have to FOIL, so patiently FOIL that out. Remember our comment at the beginning, you can't distribute a power over a sum. So over here I will get 4x squared, because 2x times 2x, and then 2x times 33.25 will be 66.5x. And then I will get a second 66.5x. And then 33.25 times itself is 1,105.5625. So 1,105.5625. And that was the, the last times the last. And that will equal 169 times 2 is 338. And 169 times 8 is 1,352. And this is looking bad, but guess what? It turns out to just be a quadratic polynomial that we can do quadratic formula on. We just have to get it in that form. So I'm going to get rid of items on this side and set it equal to 0. And there are no other squares over there, so I have 4x squared. And then notice I have a 66.5x and a 66.5x. And then I will subtract 338x. So if you're just kind of working on the coefficients there, I have two 66.5s, and then I'm subtracting 338. I get negative 205. So my linear term is negative 205. And then I have this constant, and I will add 1,352. So I will have a positive. And if I take the 1,105.5625 and I add 1,352, I obtain 2,457.5625. 2,457.5625. 2,457.5625. All right, so now I have my quadratic, and I can do quadratic formula. So remember, it's the opposite of the linear term, plus or minus that linear term squared, minus 4 times the leading coefficient times the constant, divided by 2 times the leading coefficient. So negative 205 is my linear term, so I will have positive 205. Then plus and minus whatever 205 squared is. Again, I know I didn't put the negative, but when you square, it's not going to matter. So then minus 4 times 4 times the 2,457.5625. That's my discriminant. Again, the calculation underneath that square root's the discriminant. And then 2 times 4 should be in the denominator. That looks pretty bad, but I feel like if we clean up that discriminant, it's actually going to look better than it does at the moment. Okay, so here I took the 205 square. Oops, there's an extra 6 in it for some reason. Okay, so I took the 205 squared, and then I subtracted 4 times 4 times the, messy 2000 number, and look, I get 2,704. Like I said, it probably cleans up somewhat. Okay, so 2,704 is the discriminant. So 205 plus or minus the square root of 2,704 over 8. And let's see what the square root of 2,704 is. It is 52. So I ended up with a perfect square. Okay, so 205 plus or minus 52 over 8 gives me two possible answers. One of the possible answers is going to be the 205 plus 52 over 8. So 257 over 8, or 205 minus 52, which is 153 over 8. And those are my exact answers. If we wanted to approximate them, one is approximately 32.125 and the other one is 153 divided by 8, 19.125. Now we squared twice, okay? And sometimes when you're squaring, you end up including extraneous solutions. So this is a case where you definitely want to check your answer. I know I wasn't exactly checking my answer with the other ones, although I was checking them off the graph, okay? So we need to check both of these answers. So go back to the original equation. So I kept it handy here. And we want to go back to the original equation. And it was the square root of 2 times x, so 19.125 was one of the solutions. And then subtract 8, and then add 6.5, and I should get 12. So let's see what we get on the other side. If I take the square root of 4 times 19.125 and I add 67.5, I get 12. So the 19.25 does look like it is working as a solution. Then my other solution, okay, so that again we plug 19.125 in and both are giving me 12. All right, so then if I take the square root of 2 times 32.125 and I subtract 8 and I add 6.5, I get 14. And then the square root of 4 times 32.125 plus 67.5 also gives me 14. So this was a case where both worked. Both of the solutions were accurate. Now my graph doesn't exactly show that. One was 19 point something, so that would be about right here. And the other was 32 point something, so that would be about right here. It's just the graphs are so close together in that area that they look like they're simultaneous for all of these points, but I'm intersecting here at the 19.125 12 and at 32.125 14. And if I zoomed in, I would see that they're separated just slightly at like in between those 2 points, and the only intersections are those 2 points. Our last type of equation that we're going to show in this video, again, there's infinitely many types of equations. I've tried to pick some fairly common, messier ones that show up in college algebra. I know a couple of these were a little bit messy. I'm particularly trying to show how to slog through a messy equation and get there successfully, because those would tend to be ones you might have more trouble with than ones that are super clean and easy to see what the answer is. So here we have a rational equation. So a rational function means you have a polynomial divided by a polynomial. My numerators all happen to be constants, but they're still rational equations. And when you're dealing with any kind of equation that has fractions, you want to multiply both sides by the common denominator, and that will turn it into a polynomial equation. So, or, I mean, I guess technically you could have square roots in the denominator and you might choose to do the same thing, and then it technically won't be a polynomial, it might be a square root equation. But in this case, when I multiply both sides by the common denominator, I will end up with a polynomial. So let's find that common denominator. The denominator of this term is x plus 2. The denominator of this term is x plus 3. I wonder how that factors. I won't be surprised if it actually factors as x plus 2 times x plus 3. And it does, because x times x is x squared, x times 3 is 3x, add that to 2 times x, you get 5x, and then 2 times 3 is 6. So this denominator contains both of those factors. Okay, not uncommon when you're dealing with a textbook equation, okay? But I guess out in the real world, if you created some data that gave you a rational equation, you might not have that conveniently work out. Okay, so we're going to multiply both sides by that common denominator. So the common denominator was x plus 2 times x plus 3, and I'm multiplying by 7 over x plus 2, and then that middle term, we've already shown that it factors to be both of those, so I'm going to write it as the polynomial, but we know that it's equal to x plus 2 times x plus 3. And this step looks really messy, but after we get through it, it cleans it up a whole lot. So x plus 2 times x plus 3. Okay, so cancel, 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 cancel. All right, so I'm left with 7 times x plus 3 minus 1, okay, because this whole entire denominator got canceled by both of those factors. So I'm just left with 1. And then on this side, I will have negative 2 times x plus 2. So, oh my goodness, that big messy step really reduced down to something pretty clean. In fact, we actually ended up with a linear equation, didn't we? So on this side, I can distribute the 7 through because this is a power of 1. I only can distribute over pure adding or subtracting when there's a power of 1 there. And then on this side, I will have negative 2x minus 4. And combining like terms, the 21 minus the 1 turns into a positive 20. And then I can either add 4 to both sides, or I can subtract 20 from both sides. Maybe I'll subtract 20 from both sides. All right, because that will give me 7x equals negative 2x minus 24. And then I'm going to add 2x in order to get rid of the 2x on the one side. That gives me 9x equals negative 24. And then x is negative 24 ninths. You can reduce that because both are multiples of 3. So if I divide the numerator by 3 and the denominator by 3, I get negative 8 over 3. And let us look at our graph. If we go to our graph, I can see that the graphs, you know, the blue graph is one and the green graph is the other, and they're crossing over each other at this point right here. And this is negative 5. 8 divided by 3 is 2 and 2/3, so negative 2 and 2/3. And this is negative 1, this is negative 2, so that does look like it's at negative 2 and 2/3. All right, and it actually kind of looks like they're intersecting at 1. If we wanted to know exactly where they intersect, then you'd want to plug the negative 8/3 in. I might as well plug it into this side because that side is nice and clean. So negative 2 oops, no, sorry, it's negative 6. I looked like negative 1, but I was using the one line as the x-axis and it wasn't. So I plug negative 8/3 into that right hand side. It gives me negative 6, and that certainly is what it looks like on the graph here. Here was negative 5, so it was one below the negative 5. All right, so again, if you're dealing with denominators, get rid of those denominators by multiplying both sides of the equation by the common denominator. And when you do, it will clean it up quite a bit. And in this case, that certainly was true.